in introducing this section, I'll talk about why we're here and why we should do this. And that was many years ago. I worked for Mobil, and I was a well site geologist. And back in those days, they'd send you down to Dallas for a month to have training in logging, because you were expected to do everything there on the well site. And you just had paper logs to work with. So back, I hate to say it, but back in 1975, the chairman of the Petroleum Engineering Department at KU asked me if I would teach log analysis at KU, because I was the only person he knew who knew anything about it. And I was just shocked at that suggestion. Teaching logging to students is just impossible, because there are so many interpretation problems and what have you. But nevertheless, he did persuade me. Now, why he asked me that was because the Petroleum Engineering Department at KU was having a problem. They just had the accreditation people come through, and the accreditation people said, "Where's your logging course?" And they said, "Logging course? Logging course?" And they said, "Well, you better have one by the time you get back, otherwise you'll have problems with accreditation." So that's why I wound up teaching it, and that's why they need it. It is a required course for engineering students at KU. In order to get out of the place, they have to do logging. At the same time, I also teach log analysis for the geologists in the geology department. They're not required to do log analysis at all. So they are simply expected to learn geology and then go out and make a career out of it in the real world, with the expectation that they probably get their training from companies out there. Well, maybe they're getting training out there, maybe they're not. But I teach a course in the geology department where we focus very much on what you can tell about geology from the logs. So we've got the engineers then who are working with the Archie equation to find out what fluids are there, what permeabilities are likely to be, and the rocks are kind of the background. The rocks are there to hold the fluids in place as far as the engineers are concerned. And over in the geology then, like I say, we focus on what we can tell from the rocks, which is why I have this title here, Reading the Rocks from Wireline Logs. Now things have changed a lot, and that is, for example, on this workshop we're looking at logs today from the perspective of working on reservoirs. And two things have happened. First, the logs that had been introduced in the last 30 to 40 years are very specific, tell us a lot about geology. And secondly, people are doing more sophisticated analysis on reservoirs, where it's not only simply the porosity in the fluids, but a better understanding of the geology of your reservoirs that the logs can tell you, make you a better engineer, shall we say, in working with those logs. So some of the stuff I'll show you then in this presentation will be, gee, isn't that interesting geology? But other aspects say, yes, it's not an interesting geology, but if you're an engineer, understanding some of this will make you a better engineer. So that's kind of what's going on. Now, if we focus specifically then on the kind of properties that we could get from the logs that tell us about geology, this is kind of what we're looking at. Log types, electrical logs up here, resistivity and SP. Resistivity has been around since 1927. SP since about maybe 1929, something of that sort. And geologists looked at those for many years. In fact, the very first log that was ever run was for a geological purpose. It was not run to find oil and gas. So Schlumberger's very first log that was run in Alsace-Lorraine, where the family came from, was run because they were frustrated back in those days of picking tops and bottoms of formations when they were doing cable tool drilling. That made it a little tough. So the aspect was whether it be possible to make a measurement within a borehole that would allow you to pick the top and the bottom of formation. And they were successful. In that first well, it had been cored, so they knew what the geology was, and they're able to see on the resistivity curve the tops and bottoms of formations. And it's kind of interesting then that for many geologists, that's where it stopped. They simply look at resistivity or an SP log and say, well, there's the top, there's the bottom. Let's map a structure, or let's look at an isopac, and they don't care for much of what's in between. Now, to some extent, though, you can still look at the resistivity and the SP, for example, and the gamma we'll see down here, and get an idea. If you're looking at sandstones, you get an idea of relative grain size. We'll look at those kind of aspects. Where things changed in a big way, though, was when life moved on, and that's when nuclear logs came in. So even now we talk about electrical logs, e-logs and so on, but that's just picking up the old days when that's all there was. Resistivity and SP were electrical measurements. When the gamma ray was brought in about the late 30s, that was the first nuclear log measuring radioactive properties. And now we see the other nuclear logs, the neutron and the density and the photoelectric factor and even the geochemical logs. They are counting radioactive particles, very sensitive then to the mineralogy, the lithology and what's going on there. And finally we get down to here, and this is what we'll be looking at this afternoon when we have a section what I call enhanced logging. We have electrical imaging where we can actually see. We have an electrical image in the borehole wall, and then finally NMR, nuclear magnetic resonance logging, that digs down into the various types of pore size. What we're going to talk on mostly, we're going to focus an awful lot then on this aspect right here, on the information you get from the nuclear logs. And we're not talking only about Schlumberger, we're talking about even the smallest logging company in Kansas. So you don't have to go top dollar at all. It is now a routine to have a neutron and a density log and a photoelectric factor log. Small companies do this. And a gamma ray, of course, would be standard. Let's look first at the gamma ray log. Say originally, when it was introduced, say in the 30s, the basic idea was just like having a Geiger counter lowered up and down a borehole. So people were used to the idea of using Geiger counters if you were looking for radioactive ores at the surface. So it wasn't a big stretch to think of, let's poke one down a hole and simply draw it up. Today's gamma ray tool wouldn't be quite the same as a Geiger counter. It has a scintillation crystal which is within the housing of the tool, and as natural gamma radiation comes into that tool, it causes small flashes which are counted. But it's the same general principle. So it is absolutely simply measuring natural radioactivity. Now, if this was a physics class in a university, I would have maybe a periodic table behind me, and we would look at all sorts of radioactive isotopes, you know, californium-252 or whatever. Most of those isotopes, though, are of academic interest to us in terms of their occurrence in nature. So many radioactive isotopes either occur in such minute quantities or more often have such short half-lives that they hardly exist as far as we're concerned. But the natural radioactivity comes from three major sources, and that is what's written here, the uranium series. I say uranium series or uranium family because it's not only the uranium isotopes, it's also the daughter products and the granddaughter products. It was a decay series where uranium will break down into other isotopes which are themselves radioactive. The thorium series. So again, thorium isotopes, daughter products, granddaughter products. Finally down here, a distinctive isotope, potassium-40. Now if you went to you did some geology courses, and you say you took a course on geochronology, dating rocks from radioactive isotopes, you'd be looking at the same thing. You'd be thinking of potassium-argon dating, uranium-lead dating, and so on. So the geochronologists, the geologists try and date rocks, they're actually counting from this. These are the radioactive clocks. And when we see a measurement made in the borehole, we're just simply listening to the ticking of those same clocks. And here we have a typical gamma ray log. This one is from Miami County, so up in northeast Kansas. And we see we've got a section then of Mississippian limestones down here, and we've got a Cherokee group, a mix of sandstones and shales. And here's our scale, gamma ray in API units. When gamma ray logs first came out, they were simply recorded in counts. But those count scales were specific to whatever tool was run. So if you're trying to compare one tool with another, you had the problem that, well, which tool was being run here? So clearly they needed to standardize the units. And you'll even see, not only on the old gamma ray logs in Kansas, you'll see some in counts, but then you'll see some recorded in micrograms equivalent radium per ton. So they standardize. So you say, I think you solved it, but I don't understand it, I don't know how to use it.